So I'm Yuchong from alongside, and I will present on spin transport in order performance. So as an overview, I'll first cover on some preliminaries on its setup of this experiment theory, and then we'll cover on kinetics as well as the more analytic stability response in the CG system. So we'll mainly be studying how the spin density distribution evolves and distributes in the box potential under magnetic field for fermions. So we'll prepare a fully polarized fermion gas in very low temperature, and then we'll apply a magnetic field to it. So the magnetic field will be along z direction, and we'll have a gradient along y direction. And the main purpose of this gradient is to offset gravity. And yeah, so we'll initially all the spin of the fermions will be aligned in z direction, so that's z polarized. And then we'll apply power to pulse to push them into y polarized states, and then we release the system to let it go. So intuitively, what we will observe is, of course, the different spin vectors will be set at different Raman rates because we have a gradient along y direction for the magnetic field, and the precession rate is proportional to its magnetic system. But we'll also have diffusion, and this process will be collision interaction as influenced by particle diffusion. And this is experimentally what we actually observe. So we will have spin segregation. So for instance, on the top, you see that basically all the spin are particles. On the upper part of the box, and in the lower half of the box, you have spin down. So you might expect this to be related to Stern-Gerlach effect, but actually this is not the case because the rate at which this spin segregation occurs turns out to be much faster than you predict from pure Stern-Gerlach effect. And we'll later on show that even if you completely neglect Stern-Gerlach forces, you can still have this phenomenon. So basically, we'll aim to explain why this spin segregation occurs and what are the relevant dynamics. So if it's not Stern-Gerlach, obviously there are some other mechanisms behind this spin dynamics, which is the identical spin location effect. So a semi-classical feature is that due to exchange interaction, when two particles that have similar states that comes near to each other, the block vectors will actually present around each other. As you see, basically the blue vectors will present around the red block vector, the red will present on the blue one. And in actual theory, they will present around the mean block vector in that region. So this has very profound influences. So firstly, it produces spin Z dynamics like we see. And we will also expect to have spin wave excitation due to this mechanism. So having the qualitative coverage, we can now model this system. So the Hamiltonian we'll be using will consist of the kinetic, which is H naught, as well as box potential. And finally, we have the interaction part. So the interaction part will consist of the magnetic field gradient interaction, in which case it's omega naught that is proportional to the magnetic field gradient and magnetic field strength and so on. As well as a two-body collision curve. So the G here is the S-wave scattering strength, and we see that the collision only accounts for collision between spin up and spin down. So the reason behind this is that if you have identical spin, then for fermions, the party exclusion principle will basically forbid identical spin particles to come near each other in the first place. And because this scattering process is very localized effect, we will not expect collisions between identical spins to occur because they cannot come near to each other in the first place. This is why basically we only correlate up and down spin for the collision occur. And so to solve this system with this component, obviously overcomplicated, we'll first perform mean field approximation. Then we'll use a phase-space formalism to do Wigner transformation with density matrix. And basically what we do is we solve the dynamics of this transform version of density matrix to first order quantum interaction. And this will give us a kinetic expression for a space-based distribution. There is a phase-based distribution for the magnetization, which is a function of position and momentum. So in the kinetic equation, we'll define two additional terms. One is the mean field angular velocity, which basically characterizes how strong the mean field interaction energy is. And the other is S, which is the spatial magnetization vector. So it's basically integrating the phase distribution over the space. So if you integrate that out, you will get the spatial distribution of the magnetization vector. And down here is the kinetic equation. So it has basically three terms. The first one is material derivative, which we'll see in most transfer equation. And the second term is a force term, which is the Stern-Gerlach calculus. And the final term is precession rate. So this precession obviously has the number precession, which is omega naught, as well as the precession due to the identical spin rotation effect that I mentioned, which is omega m2. So for now, we'll neglect the Stern term because we know that this term is not particularly important up to now. And box potential will enter as well enters the boundary condition. So if we simulate via the kinetics equation, we can see on the top right, on the upper right, that the SC dynamics is very predicted. So everything up on the upper half of the box is spin up, and on the lower down, on the lower part is spin down. So this we are able to predict this via the kinetics equation. But there are other things that we should notice. So firstly, we see that spin y is almost uniform, and it does not change much over time because we point all the particles along spin y initially. And also, we notice that the z direction dipole will oscillate in the decay rate very slow. And also, the SY decay rate is also very slow. So this motivates us to perform a steady state approximation in the crisis to drive more analytic results. And to do that, we will introduce the Laplace equation, which is basically if you define a spin current state, which is the integration of n times the momentum and then integrate the momentum. You can then integrate the entire kinetic equation for momentum space, which will give you the Laplace equation. So this equation has two parts. One is precession part. So you can see that partial Ts is almost equal to omega process, which is basically a precession, but you will account for current as well. And the other term is the diffusion. So you see that in the diffusion term, if you neglect S cross J, this is basically just precession, which is basically just precession, but with relaxation time top that accounts for additional depth. But this S cross J effect is exactly what is spin rotation. So this is the term that produces all the spin Z dynamics that you see in experiment and the kinetics equation. And so the Laplace equation will have mainly two results analytically. One is that we can extract the dispersion ratio for the spin rate equation. And the other conclusion is that we can basically now analytically predict the spin segregation. But firstly, the dispersion condition. If you assume a very weak magnetic field gradient for the Laplace, you will be able to extract the dispersion condition which is up there. So there are mainly two terms. One is the mean velocity square, which is v naught, and two is the wave vector, as well as it also relates to Gn, which is interaction strength. So from this, we would expect that the dispersion relation should be n-symmetric, or almost n-symmetric, if you tune G from positive to negative, which is repulsive or attraction. But this is not actually what we see from the experiment. So from the experimental data which is down here, the blue points are attractive and the red points are repulsive. You see that there's a systematic offset between the theory and the attractive touch, but this does not occur that much for repulsive. So this is one of the anomalies you see, which is that the system seems to have an asymmetry between attractive and repulsive touch. The other case is the linear response for the dipole amplitude, which is the spin Z dynamics that we saw. So if we clone a multiple cell expansion on the Laplace equation to second order in the magnetic field gradient, then we can basically arrive at a quasi-steady state solution for the Z part of the state of the magnetization density. So this is the expression. So within the first bracket, we see that the first two terms are exponentially decaying plus oscillation. So this is why you see that the oscillation part is decaying. And this decay is very, very fast. So the decay rate of the oscillatory transient part is exactly the rate at which the spin Z dynamics will diffuse. And it basically characterizes how fast we can start to observe spin Z segregation. And in fact, if you tune the decay rate to be very, very slow and tune out the steady state decay rate, then you will not be able to see spin Z dynamics. And that leaving out the exponential decay rate, we see a steady state, which is basically the steady spin Z segregation that we see in experiment. And finally, we have a sign term that characterizes why we only see one spin up and one spin down component, because only the first four moves is important. So on the down, we are fitting the theory with very good. So now we aim to resolve the asymmetry between the frequency between attracting and repulsive. So it ends up, if you recover the circular action from the kinetics equation, and then you rederive the Laplace equation, you will get that the velocity is not changed by Gn over Gn. So Gn is the interaction strength. So this accounts for the asymmetry between repulsive and attractive. So and it ends up that the sun direction itself does not lead to spin vibration, but it affects the repulsive and attractive branch with the entire motion. So now on the down, you can see that for amplitude and frequency, well, we are able to predict this asymmetry between traffic and pulse. So finally, on pulse load, basically, we can look at nonlinear spin wave just beyond the linear response. We can also look at beyond mutual correction. And finally, some more complex momentum and space issues for the spin dynamics when nano damping occurs. So here are my references, and thank you.
There are some experimental reasons why
you mean chips moment? I'm not sure for that. Yeah. But we do have reports. I'm not sure what we have attracted.
On normal slides at 11, we said only the first few terms of the Fourier series are that because of applied hypothesis.
Not exactly, because the strength of each order component is determined by the prefactor of the bigger number case, right? And this term turns out to be scaling as n to the power of 4. So, which means that basically all the higher forms are members.
Is this what's still stage 3 unit to change, correct?
Sorry?
Those the exponential unit to change, next.
Yes, if you change your external field to very strong, the x component and the y component will have higher forms, but not very z direction.
Further question?